Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 8, 2025, about a week ago. It introduces a model that can reconstruct large three-dimensional scenes from tens to hundreds of images in a single forward pass, processing up to 128 views in under 1 second, while staying within about 0.7 decibels of much slower optimization-based methods that it can beat by over 250 times in speed. The paper is titled Multi-View Pyramid Transformer, Look Coarser to See Broader. And as we will see later, the results are really impressive for fast, scalable three-dimensional reconstruction. Alright, Figure 1 gives a visual sense of what the method achieves at scale. The montage of 5-point cloud scenes shows that the model reconstructs complex environments from 16 up to 256 input photos, and each panel labels that this happens in, at most, about 2 seconds. The graph on the right plots quality versus time and shows that the new method is both about 9 times faster and roughly 5 decibels better in reconstruction accuracy than the two prior models. Alright, Figure 2 explains how the model actually processes many views efficiently. The bottom row of orange grids represents high-resolution frame-level tokens, where each image is handled separately but with rich spatial detail. The middle green row shows group-level tokens that summarize several neighboring views, so the model begins to reason across cameras. The top blue row depicts global tokens that attend over all views at once, but at a coarser spatial scale. On the right, the vertical blocks indicate pyramidal feature aggregation, and the final dense prediction head that turn these multi-scale tokens into a full three-dimensional reconstruction. So, after Figure 2 laid out the architecture, Table 2 shows how that design performs when scenes are covered by almost 200 or more views. The table compares reconstruction quality and runtime for 192 and 256 input views on the DL3D versus dataset. The baseline three-dimensional Gaussian splatting reaches around 30 decibels, but needs about 8 minutes per scene. Long LRM actually runs out of memory at these scales. Our method matches or slightly beats the baseline quality at roughly 30 decibels, yet finishes in under 2 seconds, which highlights the scalability advantage. So, while Table 2 focused on dense supervised settings, Table 3 reports zero-shot generalization to the Tanks and Temples and MIPNERF 360 datasets. The table lists results for 32, 64, and 128 input views, comparing long LRM, ILRM, and the new model. Across all view counts and all three metrics, the bold numbers show that the new method wins consistently. The performance gap grows with more views, which indicates that the hierarchical design scales gracefully, even on unseen datasets. Well, Table 1 steps back to the DL3D versus dataset and compares methods across 16 to 128 input views. The table reports reconstruction quality with peak signal-to-noise ratio, structural similarity, and LPIPS plus runtime. Three-dimensional Gaussian splatting delivers solid quality but needs about 8 minutes per scene. Long LRM and ILRM are faster but noticeably worse in accuracy. The new model consistently achieves the best or tied best quality while staying under 1 second, even at 128 views, so it dominates the efficiency-accuracy trade-off. Well, Figure 6 turns from quality to raw speed. The two plots show inference time versus number of input views, and together they highlight how crucial the hierarchical design is for efficiency. Panel A compares the baseline to variants that replace group attention with only frame or only global attention, and those alternatives become noticeably slower as views reach 256. Panel B goes further, revealing that removing the interview, or full dual hierarchy explodes latency to tens of seconds, while the full model remains under a few seconds. Alright, while Figure 6 dissected internal variance, Figure 7 compares full methods head-to-head on speed. The green curve for the new model stays under about 4 seconds, even at 448 views, so latency grows very gently. The orange ILRM line rises steeply past 60 seconds, and the blue long LRM curve hits an out-of-memory wall beyond roughly 192 views. This gap shows that only the hierarchical design truly scales to hundreds of images in practice. So the big takeaway is that this multi-view pyramid transformer turns hundreds of photos into a high-quality three-dimensional scene in a single, very fast pass. By mixing fine detail within each image with coarse, global reasoning across all views, that kind of scalable multi-view understanding could spill over to robotics, mapping, and generative video. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.